In this section, we're going to be studying Archimedes' principle. And it says any fluid applies a buoyant force to an object that is partially or completely immersed in it. The magnitude of the buoyant force equals the weight of the fluid that the object displaces. So what we have here is an equation that says F sub B, which is the buoyant force, equals the weight of the displaced fluid. And so that's important to remember, that's the fluid being displaced. It's not the weight of the object, it's the weight of the fluid displaced by the object gives us what the buoyant force is. What happens is the object in the water or in the fluid pushes the fluid to the side, and that fluid wants to go back to where it was, and so there's this force acting on it. There's this force acting on the object. An example of this would be anyone who has tried to push a beach ball into the water has felt how the water pushes back with a strong upwards force. This upward force is called the buoyant force, and all fluids apply such a force to objects that are immersed in them. The buoyant force exists because fluid pressure is larger at greater depths. So the further down you go into the fluid, the larger the force acting on you will be. So what happens is, if this object is underwater, there is a force from the water on top of the object, and there's a force from the water underneath the object. The force underneath is larger than the force on top, and that's why there's a buoyant force. That's why the difference between those two forces is that buoyant force that causes this to push up. So an object of weight 100 newtons is being immersed in a liquid. The deeper the object is, the more liquid it displaces, and the stronger the buoyant force is. In the second picture, the buoyant force matches the 100 Newton weight, so the object floats. 100 Newton weight down, the buoyant force is up. We have a problem here. I want you to pause the video and see if you can solve this problem here. It says a solid square pine wood raft measures 4 meters on its side and is 0.3 meters thick. Determine whether the raft floats in water, and if so, how much of the raft is beneath the surface. See the distance h in figure 11.19. In order to do this, you're going to have to know a couple things. We need to know the density of the pine is 550 kilograms per meter cubed, and the density of the water is 1,000 kilograms per meter cubed. And then with that, you can go ahead and solve this problem. So pause the video and solve it. The way we should look at this is to see, okay, well, how much does the pine actually weigh? And we're going to use this equation, density times volume times gravity equals the weight of the raft. The weight of the raft is actually mass times gravity. Now, mass is density times volume. If you look at the density formula, density equals mass over volume. So if you solve for mass, it's density times volume. And so you get this here, and it's 26,000 newtons. And let's look at the maximum buoyancy that we can have. The maximum buoyancy, again, it's the mass times the gravity of the water. It's the water that's been displaced. It's mass times gravity of the water. It's density times volume is your mass times gravity. That gives you 47,000 newtons. So yes, since the maximum possible buoyant force exceeds the 26,000 newtons of the raft will float only partially submerged at a distance h beneath the water. So let's find out what that distance h is. If you haven't found that out yet, pause the video and see how much water must be displaced in order for the buoyant force to equal the weight of the raft. In other words, how much force has to be displaced in order to get 26,000 newtons. So pause the video and go ahead and solve that. If you're having problems, your hint is you're going to use a very similar equation, and you're going to use the density of water because that is what's being displaced. Remember, the buoyant force will equal the weight of the water. So go ahead and try that. What we have here is the weight of the fluid, the weight of the water, equals density of the water, volume of the water, times gravity. The volume of the water is length times width times height. It's 4 meters times 4 meters times the height. And we know it has to equal 26,000 newtons because we want that weight of the fluid that's been displaced to equal the weight of the raft. So you go ahead and you have 26,000 newtons equals density times volume times gravity. And now you go ahead and plug in your numbers and you can solve for your H value of 0.17 meters. A ship floating in the ocean is a familiar sight, but is all that water really necessary? Can an ocean vessel float in the amount of water that a swimming pool contains, for instance? So the question is, well, how much water does this boat really need? Does it need the whole ocean, or how much water does it need in order to float? So pause the video and think about that answer. Well, what it needs to float is the amount of water that it has displaced. This amount of water that it has displaced equals the weight of the ship that's floating. So all you need to know is that this water, if you want to put it into a canal, if you can fit that water into the canal and have it come up to the top perfectly when this pushes inside the water, then this is really all the water that you need to float that ship. Here's another problem that we have here. Normally a Goodyear airship, such as that in figure 11.22, contains about 5.4 times 10 to the third meters cubed of helium, whose density is 0.179 kilograms per meter cubed. Find the weight of the load, WL, that the airship can carry in equilibrium at an altitude where the density of air is 1.2 kilograms per meter cubed. So they just basically want to know how much the weight of the blimp is going to be in order to, for this helium, how much is the weight of the helium and the blimp and everything? But when they say load, they just mean everything together. How much of that can, how much can that be in order for the blimp to be held up in the air? And remember, the air is what's being displaced. So, and let's assume that the volume of the blimp is the same as the volume of the helium, that it's mostly all just the helium. So the volume of the blimp is just that. So I want you to go ahead and find out what the weight of the blimp is. So pause the video if you want to go ahead and try it. Otherwise, I'll give you hints along the way, and as you want, just pause and see if you can finish the problem off. The first thing we have to do here is get an idea of what the free body diagram would look like. We have the buoyant force up, we have the weight of the helium, and the weight of the load, and they mean by that is just the weight of the blimp and the people in it and everything. So the buoyant force is what's holding up. The helium has weight. Remember, the helium, yes, it is less dense than air, but it still has weight that's being pulled down by gravity. So we're going to use this idea here to set up an equation to help us solve this problem. We have the weight of the helium plus the weight of the load equals the buoyant force. That's what this says right here. Or we can arrange things and say the weight of the load equals the buoyant force minus the weight of the helium. So now we're going to go ahead and plug in our values. Remember, it's mass times gravity, which is the mass is density times volume in these types of problems. So if we go ahead and plug in our values, we see the weight of the load equals the buoyant force, which is density of the air, the volume of the ship. Now the volume of the ship is this 5.4 times 10 to the third. It's not really the volume of the ship that we want, it's the volume of the air that's been displaced, which is the same as the volume of the ship. So that's why they say volume of the ship, but it really is volume of air displaced minus, now we have the weight of the helium, that's rho density times volume times gravity. Again, the volume of the ship is the same as the volume of the helium. And we'll go ahead and now just plug our values in, and we end up with 5.4 times 10 to the fourth newtons is the maximum weight that we can have and still float in air. That's 1.2 kilograms per meter cubed. Okay. So the biggest thing we've learned in this lesson is that the buoyant force, the magnitude of the buoyant force, equals the weight of the fluid displaced. And remember, fluid can be a liquid or a gas. It can be either one. It's equal to the weight of the fluid displaced. And the other thing one of the big things we learned is the new equation. And the other big equation is that the buoyant force equals rho Vg. And this equation comes from the idea that density equals mass over volume. We solve for mass, and we get mass equals density times volume. And if we come over here, this section right here, that right there, is mass. So really the buoyant force is mass times gravity. It's the weight, it's the mass times gravity of the fluid that's been displaced. So all this is from the fluid that's been displaced. We have to realize that the density and the volume of the fluid that's been displaced.